Okay, so this time I'm going to start to deliver on my promise to describe the modern foundations of mathematics by talking about simple type theory. So we're finally going to start looking at this fascinating area of type theory, and we're going to see how from a few assumptions and rules for symbolic manipulation we can describe all sorts of structures in mathematics in a totally precise kind of computer-friendly way. So I'd like to talk a bit about where we've gone in this course and where we're going. So we started out by looking at some ideas from category theory, in particular some kinds of universal constructions, products, co-products, exponential objects, terminal objects, initial objects. We've been covering these kind of fundamental ideas from category theory that can be used to encode all sorts of data structures. And the next thing we were doing was looking at how these kind of things appear in logic. We've been studying things like these kind of partially ordered sets representing subsets and thinking about how ideas from logic can be described. And in doing so, we've been thinking about hating algebras and actually moving towards type theory. And now finally we've got to the point where we can actually look at all of the rules behind a particular type theory. So there are various different kinds of type theories with different kinds of rules and different sorts of levels of sophistication. But what I want to look at is something which is sometimes called simple type theory. So this is what we're going to do today. Now there's various reasons why this is a good thing for us to look at. One of them is that it's pretty simple. Okay, it's a little bit more complicated than the hating algebras that we're looking at in logic, but it's very directly related. Basically, the kind of type theory that we're going to look at is the sort of theory of how one can represent general Bicartesian closed categories. These are the categories that have all of the sort of categorical gizmos which we encountered before within them. And so these kind of general Bicartesian closed categories, we can think of them as describing what's going on in set theory, or we can think of them as describing what's going on in logic. We can interpret them in many ways. But the point is that everything that we do is defined by really definite rules that we can completely kind of understand. And it really allows us to get a sort of language which we can actually put in a computer. In fact, towards the end of this video, I'm actually going to talk about how one can literally write a computer program which can deal with this kind of simple type theory. Now, how is it as a kind of foundation for mathematics? Well, not bad. Okay, you can do a lot of mathematics. You can describe a lot of thought in terms of this simple type theory. There are some sorts of limitations to it, and this is why the kind of modern approach is to work with something a bit more sophisticated called dependent type theory, and we're going to get into that in the future. But I think for starting out with type theory, I think this is a really interesting thing to look at. And also, as you shall see, there's so much going on and so many different directions that you can explore. I think it's really a good idea to start with a so-called simple type theory, because it's already rich enough that you can really explore this kind of structure for a long time. And because we have this kind of threefold symmetry between these different subjects, all of these ideas that we're going to encounter in simple type theory are sort of reflections of things. We can think of them as things from category theory or things from logic, but it's just like the same kind of ideas being reflected between these three different disciplines. And so it's really worthwhile to focus on this stuff. So really what we're seeing in this video, what we're going to see, is a kind of subject which On one hand, we can think of it as pure mathematics. We can think of it in some sense actually as much purer than a lot of mathematics, because the idea is that all of the kind of symbols and rules are totally defined all the way down to the bottom. And so it's really very pure in the sense that it's very clear what everything means and it's very clear what you're allowed to do. So that's one good thing about this. It's simple type theory is a great thing to learn if you're interested in the foundations of mathematics. And in addition to being really useful for understanding the foundations of mathematics, these ideas are also going to be very useful for understanding computer programming. I mean, a lot of these kind of programming languages built on type theory are really just built on slightly more elaborate kind of ideas of the same kind that we're going to be seeing today. So really what I'm trying to say is that type theory is really worth learning, not just from a sort of mathematical perspective, but also from a sort of technological perspective. Now in this video, I'm going to talk about simple type theory. Now the idea of this is it's a really kind of stripped down basic type theory which has just what's required to be able to model what are known as Bicartesian closed categories. Now these are special kinds of categories that have certain sorts of categorical gadgetry, in particular terminal objects, products, initial objects, coproducts and exponential objects. And these are in a sense sort of the basic operations of category theory, which allow us to form data structures, and most of the things that we do in set theory and logic and all the rest of it can be pitched in terms of those things. So the ability to capture all of these ideas in a formal system is going to be extremely useful. And there are so many benefits to doing a simple type theory. The idea basically is that we want a sort of minimalistic language for describing these Bicartesian closed categories. And so we just want to be able to talk about these different kind of gadgets and operations, but that's it. And so we have these formal rules and we're able to express everything symbolically. So on one hand, we gain that kind of precision because we end up with a theory that's so precise and sort of just involving symbol manipulation. So we can literally encode it in a computer very easily. But on the other hand, our theory itself, well, we can ask, what does our theory mean? What are we talking about? This idea of having a way to formally manipulate symbols, which can be interpreted in many rather different kinds of ways, is a very sort of sophisticated modern approach to doing mathematics. I mean, if you can simultaneously describe sort of the important things that are going on in set theory and the important things that are going on in logic with one theory, one sort of way of manipulating symbols, if you only need kind of one proof to show a result in set theory and a result in logic simultaneously, you would want to do that, right? And that's what we're going to do. There's really a lot of advantages to this kind of language. It's formal. It's pretty simple. There are not that many rules, and once we get used to it, we'll see that manipulating the rules is, you know, really quite simple. That's why we're actually able to put it into a computer in a sense. We don't have to sort of sit back and wonder about the meaning of all of our expressions and what type of manipulations we're allowed to do. It's all very much black and white, which is a really great thing. As we say, it has many interpretations. So I shall list a few important Bicartesian closed categories. There is set, the category of sets. And there is a category called cat. This is the category of categories. It's fascinating structure to people interested in category theory, and that's also an example of a Bicartesian closed category. And then of course there are these Heyting algebras, which allow us to be able to model things in logic. And another good reason to learn about simple type theory is that it really helps us to understand category theory. And another good reason is perhaps if one's interested in computer programming languages, as I am. It's quite an interesting thing learning type theory. I mean, for myself, I sort of got into it partially because I wanted to improve my mathematics, understand foundations better, understand connections with category theory better. But then all of a sudden, when you're learning type theory, suddenly you know how to program your own language. It sort of, for me, it was a surprise. I sort of woke up one morning and realised that all of these type theory rules that I was learning could be used to make a computer programming language from the ground up. And this is a really interesting kind of aspect to this. And my opinion is that if one wants to set up a computer programming language, these kind of simple type theories are a really great place to start. So basically the idea is like this. We have these kind of elementary gadgets of category theory: terminal objects, initial objects, coproduct, product, exponential objects. And if you sort of do a fair amount of category theory, you'll notice that, number one, categories with these kind of properties are everywhere. There's just so many categories which have all of these different properties. So I'll try and list a few off the top of my head. The category of graphs, the category of functions, the category of sets, the category of topological spaces, the category of categories, the category of partially ordered sets, the category of simplicial sets, the category of finite sets. I could go on. There's absolutely hundreds of useful categories that are Bicartesian closed categories. And the thing is that, in a sense, what make them tick are these kind of aspects of having these kind of special properties. Things like having terminal objects and products are the kind of things that we use all the time. Exponential objects too. Very, very useful. So the thing is that this kind of type theory we're going to be learning about uses these kind of bare basics, these certain properties which are common to all these categories. And basically the idea is that we have this sort of language by which we can combine these different notions to make more complex things. So let me give you a little example. Okay, what about the idea of arrow composition? Well, we can represent the arrows from A to B as this type here. We'll get into this later, but basically this means the same thing as b to the power of a. It's notation essentially for an exponential object. So if we're thinking in set theory, this will be the set of arrows from A to B, and this will be the set of arrows from B to C. And there's a function which takes in an arrow from A to B and an arrow from B to C, and gives us an arrow from A to C. This is the function which defines how arrow composition works. Now I'm not going to get into the details yet because it's too early, but notice here that what we're sort of doing is we're using ideas of products and exponential objects, and it turns out that we can express this sophisticated idea of function composition using these notions. So this is just one of the many examples where we can use the kind of gadgetry within a Bicartesian closed category to sort of build up some quite sophisticated ideas. And as I've already said, all of these kind of proofs in intuitionistic logic can be done by manipulating these kind of elementary gadgets and so much more. Now, of course, if you're dealing with a particular category, let's say cat or set, yes, it will be a Bicartesian closed category, but I should also say that if you're dealing with a particular Bicartesian closed category, like, let's say, cat or set, yes, it will be Bicartesian closed. Yes, anything that we're going to be able to talk about in our type theory will be true of such a thing, but there may be added sort of special features of that category. And if we want to model these kind of special features of a particular category, we may have to sort of add in some extra axioms into our system. But we're not going to get into the details of that at the moment. Right now, I just want to talk about how we can do this kind of simple type theory. And I think it's a great idea to take this very seriously and to really think about how you can implement these kind of rules on a computer. Now, I'm going to try and cover most of the details of this theory, but I don't want to get really into the kind of minutiae of it. So I shall add a link to a paper which you can read, which covers the theory in a much more sort of precise manner, so that if you want to, you can actually implement this kind of thing on a computer. And so what we're going to talk about, I like to call it simple type theory. We could also call it lambda calculus with sums. Okay, so I think one of the things that makes type theory kind of hard to talk about at the beginning is that the things in it have so many interpretations. So I could talk until the cows come home about different ways you can think about these different terms and types and contexts and so on. But at the end of the day, the important thing is really just the sort of formal rules of the thing. So let me tell you the formal rules. Now, we have all these different types, which we typically write as capital letters. And in particular, we have an empty type. Now, in set theory, you can think of that as the empty set. In logic, you can think of that as the false proposition. We also have the unit type, which you can think of as the terminal object in category theory. You can think of it as a singleton set with a single element that we could call star in terms of set theory. And you can think of this as a true proposition in terms of logic and so on. And we also suppose that we have a list of other things, so-called base types, A, B, C and so on. And we can think of those as representing other objects in this kind of Bicartesian closed category that we're trying to model. And in addition to all of this kind of stuff, if we take any two types, then we can form the so-called product of those types. And so this is called a product type. And we can also form the coproduct, which is called the sum type. And we can also form the type of functions from a type A to a type B. And that kind of acts as the exponential object. So in terms of set theory, this is like Cartesian product of sets, sum of sets, and set of functions from A to B. In terms of logic, this would be A and B, A or B, and A implies B. And these are the basic rules for type formation. So when I talk about types, I mean something that you can form using these kind of rules by getting these kind of things and maybe combining them with these different sorts of operations. Now, the next thing to talk about is the idea of a value of a type. So if I write x colon A. Now this is a bit rough, but the way I like to think of this is that x is an arrow into A, all right? But there are various ways you might want to think of this. If you're thinking in terms of set theory, you might like to think that this means that x is a value of type A. So A is a set and it has this value x in it. Or you could think that A is a proposition and x is a proof of that proposition. And this kind of expression is usually called a type declaration. So we're declaring that this x here has this type A. Okay, so there's another very important idea for type theory, and that's this idea of variables. Okay, so It's a bit like when I was writing this idea of x plus 2, which is a number. In that case, we want x to be some number as well. So we probably want to write this kind of thing. In the context where x is of the type number, x plus 2 is also of the type number. Okay, so in order to be able to say things like this, we want to have variables. So whenever we have a type, we're going to assume that we have a load of variables of that type. So we can kind of make them up. We have as many as we want. So we could, for example, suppose we have a variable x1 of type A. Or we can have a variable x2 and so on. And so we basically have this ability to make symbols and call them variables of whatever type we want. And we can do that as many times as we like. Just like in ordinary mathematics. But very often when mathematicians are talking about something which is they want to leave as a kind of generic thing, they just pull out a symbol like x, and then they say something like, you know, let x be a matrix, and then blah, 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 blah. And that x just sort of stands for a general matrix. And we're going to assume we can do something similar with any of these types. We can just make sort of variables, which we're assuming are sort of, when we write this, we mean we have a term of type A, but we're not really saying which term this is. The next thing is the idea of a context. So I'll often write symbols like gamma or maybe delta to denote a context. And what a context is it's just a list of declarations that we have variables of different types. So I'm talking about something like this. And we can think of this as providing a sort of background for a particular judgment. Now, a judgment in simple type theory is basically when we say, in this context, that happens. So here's a typical example of a judgment. Okay, what we're saying is that in this context where we have these variables x1 of type A1, x2 of type A2 and so on, we have this term R of type B. So what we're really saying here is that we have this so-called term R of type B, and that it may depend upon these sorts of variables. So I'll give you a nice simple example of one of these sort of judgments now. What I could say is, in this context or in this situation where we have these variables, that entails that we have x1 as a term of type A1. Okay, so basically if we have this stuff, then we can form this. And so here we have this term, but notice that it depends on these variables. Well, in particular, it depends upon this variable here. I'll give you another example of this sort of thing. So here's another example, and that's saying that in this context where we have all these variables, we have that this term here, x1 comma x2, is of type A1 times A2. Now, I don't expect you to know fully what this means yet because I haven't gone over the formal rules. And in fact, the kind of idea about what sort of judgments we can make all comes sort of organically out of the formal rules of the system. So in a sense, you don't really have to understand what this means yet. But anyway, I'll give you another example of a judgment. So here's another example. In this context where we have all these variables, that entails that we have this value star of type 1. Now it turns out that we can always produce a value star of this unit type, and we can do that in any context. Okay. Now how can we think of this in terms of set theory? We can think that we're really defining a sort of function which depends upon these different values from A1 and A2 all the way up to AN, but no matter what values we put into our function, we always get this value star out. Okay, so we can think of this really as telling us that we have a function from this sort of product of these different sets that then gives us this sort of value in our singleton set. In other words, it sends all of these values in this thing that we get by producting all these sets together, and it just sends all of those values to this star value. Okay, so this is this unique function that goes into our singleton set / terminal object, and that's encoded by this kind of expression. This type of judgment as well, we could also think of this as a function, okay? This is a sort of projection, if you like, from this product of objects that's giving us this value of type A1. And so the message I'm trying to get across is that when we have this sort of statement here, which is the usual sort of thing that we manipulate in this simple type theory, that we're saying that in this context where we have these variables declared, we have this term R of type B, we can really think of that as specifying an arrow from this kind of categorical product of all of these objects to this object B within our Bicartesian closed category. Okay, so this idea of judgments is really the sort of main thing we're going to be talking about. And you can sort of think of a judgment, I mean, if this simple type theory is a game, then a judgment is a sort of stage of the game, okay? Because what you're really doing is sort of moving from judgments to other judgments by sort of playing the games of type theory. And that involves applying these sort of inference rules, which we represent using horizontal lines. And this is pretty much the same as we saw in the video on logic and partially ordered sets, where we were talking about how we can think about Heyting algebras using this kind of horizontal line notation. And basically it just means that if we have this and we have this, then we can get this. Okay, so it's a kind of if-then statement really. If this is true and this is true, then this is true. And so we have these judgments, and they're normally going to be judgments about type declarations, like saying that this term R is of type B. There's another kind of judgment that we do see sometimes, and that's an equality judgment. So sometimes we're interested in making judgments like saying that in this context, this term R is equal to this term R dash, and these are two terms of type capital B. But we'll get into that later. But this is really the sort of main thing that we see in simple type theory. So we'd be writing something like gamma to denote a context, and when we write an expression like this gamma could be any context, and this is giving us one of our kind of rules of our system. And what this says is that if we have any context gamma, which entails that little a is a term of type capital A, and gamma entails that little b is a term of type capital B, then gamma also entails that we have this term that we can write as little a comma little b, and that this is a term of type a times b. So this would be one of the sort of underlying rules of our theory which we can apply. And the idea is that we can actually sort of define the meaning of things like this idea of being able to pair terms together to form other terms. We really define what that means by talking about inference rules. So the idea is that we're going to talk about what's happening in the category theory of Bicartesian closed categories by introducing rules like this, which are encoding the different ideas, like the idea that the kind of things in a product can be considered to be pairs. So let me just give you a quick example of how we can think about this kind of thing in terms of category theory. So we can just pick some context gamma to use. So maybe we say in the context where we have a variable x type h. And now what's it mean to say that we have a term a which might depend upon this variable x of type h? Well, this is a little bit hand wavy, and I'll make this precise later, but basically we can think of little a as a kind of arrow from h to capital A. And similarly, little b, we can think of it as an arrow from capital H to capital B. And what this is then saying is that given this stuff, we can form this arrow a comma b, which is an arrow from capital H to a times b. And we know that this is one of the things that we can do in category theory, and we're sort of encoding it in type theory like this, using our idea of contexts and sort of declarations of terms. And basically all the kind of inference rules like this that we introduce enable us to talk about all of the kind of machinery of category theory, and then we can interpret these things in different ways. So we could interpret this in terms of set theory. We could say that, well, if we have a term little a of type capital A, which might depend on a variable x of type h, that's kind of giving us a function from h to a. If we also have a function from h to b, then we can form this function like this into the Cartesian product of the sets a and b. So we can also think of this in terms of logic, right? We can think that if having this evidence x of proposition h entails that we have this evidence little a of proposition capital A, and it also gives us this evidence little b of this proposition capital B, then we can form this evidence a comma b of the proposition A and B. So basically this is saying if I have a proof of A and I have a proof of B, then I can form a proof of A and B. Now this is the basic setup. Now it's a good idea to be patient when you're seeing this kind of simple type theory for the first time, because really you want to see everything and then the meaning of everything makes sense, because it's a bit like learning to play a game like chess, right? Once you know all the moves of all the different pieces, then you can understand how to play the game in its totality. And it's very similar with this simple type theory. So once you've seen all the formal rules, you can then kind of interpret the meaning of all of the different things in the theory. Okay, so I thought it was a good idea to show an example here of an inference rule. And sometimes I call this the case rule. Okay, so the idea basically is that if we have a context like this one, where we have all these different variables, x1 of type a1 and so on, all put together, then for any I, this entails xi is of type ai. So it's kind of like the idea that this context entails any particular type declaration within it for some I from 1 to n. Now another way that we could write this rule is we could write it like this. And the idea of this notation is that this gamma here stands for some context and this delta here stands for some context. And then we're just sort of sandwiching this xi of type ai between these two contexts and sort of joining them together to make this larger context. So basically we have this idea that if we're forming this larger context and it's got xi is of type ai in the middle, then that entails xi is of type ai. So this idea gives us this idea in the special case where we have that this context gamma is this type declaration of variables from 1 to I minus 1, and that this context delta is the sort of variables after I. And then the reason why we're putting this rule underneath a kind of horizontal line with nothing above it is to emphasize that we don't need any assumptions in order for this kind of thing to be true. We always have this kind of situation where a context entails any particular kind of type declaration within it. And we can think of this in terms of category theory as basically saying that we have kind of projections from these situations where we take the categorical product of many objects. So let's start to cover the rules of this simple type theory properly then. So the thing that we're mostly talking about are these kind of judgments here. So here we have a context, which is a list of type declarations for variables. So for example, the variable x1 is of type a1, the variable xn is of type an. And then we say that this entails some other declaration, like often another type declaration, like in this case that little b is of type capital B. And this is really the sort of this is really the sort of usual thing that we're going to be manipulating in this simple type theory. And there's many ways that you can think about what a judgment like this means. My preferred way of thinking about this is that this is specifying an arrow, because each type in our theory corresponds to an object in our Bicartesian closed category. And if we form a product of all of these kind of objects from the context, then we can sort of think of this expression here as defining an arrow like this, because what this is saying, if we think about this in terms of set theory now, we can think, well, what's happening is that we have this expression b, this term little b of type capital B, and it may have these variables from x1 to xn. So basically we have this little b that depends or may depend on these different values of these from these different sets. And so really it's specifying a function which is going to take in a value from each of these sets and return a value little b of type capital B. And so it's defining a function, and it's really this kind of thing. We'll see later when we get on to exponential objects how we can actually formally go from this kind of expression to this kind of expression. I mean, that's one of the beauties of this type theory. It sort of lifts itself up by its own bootstraps, and it can explain what it means by following the symbolic manipulations. There's also a way of thinking about this in terms of logic, to say that if we have a proof x1 of a1, and if we have all these proofs, so we also have a proof xn of proposition an, then using that we can get a proof little b of this proposition capital B. Okay, so what I'm going to do to lay out this simple type theory. So firstly, I'll talk a little bit about some structural rules, and then we'll get into the particular rules for describing how all of the kind of gadgetry from Bicartesian closed categories works. Okay, so I'll start by talking about this. I've already said about this rule, but I just want to lay it out again. So I'll start by talking about this kind of inference rule here. I've already mentioned it, but I want to talk about it again briefly. Okay, so what this basically says is that if we have a context gamma, so we have a list of sort of type declarations of variables, and then we have a declaration that this variable x is of type A, and then we have another context gamma, so this is another list of type declarations, and we sort of join all of those things together to make a big context, then that entails that x is of type A. And it's obvious really, because that's part of our context. So this is sort of like some kind of a memory ability, or some kind of ability to extract special cases. So I'm calling this rule case. Okay, and the idea is really quite simple. In terms of kind of logic, we'd be saying that, well, we have this list of proofs of propositions, and amongst them is this proof x of proposition A, and therefore that entails that we have a proof x of proposition A. In terms of set theory, well, let's look at a particular example of this. We'll set this context gamma to be empty, and we'll set this context delta to just consist of a value y of type B. And so we know that this is true. So when we write this horizontal line here, we're saying that from nothing, we get that this is true. And what this is really saying is, and the way we can really think of this is that it's giving us a projection. Okay, it's saying that if we have a value x of type A and a value y of type B, then we can get value x of type A. So as a function, this is something that takes in a value of A and a value of B and returns a value of A. And in fact, it turns out to correspond, as we'll see later, to the kind of projection function pi1 associated with the products. Okay, now you can't really see that at this point. Really, the way that these rules work sort of falls out as a consequence of the way that they interact with each other. So you'll have to be patient to wait for the whole theory to be rolled out, and then you can sort of do proofs and verify that things work the way you imagine them to. So that's our first rule. Our second rule is another one of these kind of structural rules which allow us to manipulate the rest of the things that are going on. And this is an idea called weakening. So the idea here is basically that we can add in variables to the context of something. So suppose we have these two contexts, gamma and delta. So those would be lists of type declarations of variables, like this kind of thing. And we're sort of joining them together to make one big context. And we're saying that that entails that we have a value b of type capital B. And what this rule is saying is that in such a case, we can then kind of add in this type declaration that this variable x is of type A. We can add that into the context, in the middle of the context. And we also get this new kind of judgment here that this kind of bigger context also entails B. So to think about what this means, well, you can think about it in logic. It's pretty straightforward. It's like, well, if you have a load of knowledge about proofs of particular theorems, and you know that together you can use those to get a proof little b of a proposition capital B, then if you have knowledge of an extra proof of an extra result, so if you add in this to your sort of book of theorems that you know, then you can still prove that little b is of type capital B. It's just extra knowledge. It's not going to impede your ability to demonstrate anything. In terms of set theory, what this is saying really is that if you have this kind of function that takes a value in b, and it may involve all sorts of variables, and then you need to sort of add an extra variable, you need to sort of add an extra kind of value to your source. You can do that just by using a projection. So here's a sort of specific example of this result. We'll take the case where gamma just consists of saying that we have this variable z of type L, and we'll also take delta to be the empty context. So this is a special case of this rule, and we have it here. And what it's basically saying is that if we have this value b, which may depend on this value z of type L, so we can think of that in terms of set theory as a sort of function from L to b, because the value that b takes may depend on this value z of type L, so it's like a function. And then this weakening rule is saying that we may want to add in this extra sort of variable x of type A into the sort of source of this function. And if we want to do that, we can make a function from L times A to B just by putting a sort of projection pi1 before we do our function. So this is sort of like saying, okay, you have a function, but I want you to make a function which has this extra input, x of type A. And then you can say, okay, fine, I'll just do a projection to get rid of that x of type A, and then I'll do my original function anyway. And that's the kind of idea in terms of category theory. So notice that these different rules of what's going on have interpretations in terms of category theory. I mean, that's really the whole idea, is that we're sort of modelling Bicartesian closed categories, so we can think about what we're doing in terms of diagrams. So it really just kind of gives us more ways to think about the same thing. So okay, these are enough kind of structural rules and meta theory for us to begin with. Now we can really start to talk about the essence of this simple type theory, okay? So let's now talk about unit types. So remember our unit type, we write that as 1. And we assume we have a unit type. And one of the things about types is that sometimes we want to be able to talk about the values of those types. And so we want to do everything with these kind of formal rules. And so we have so-called introduction rules, which allow us to basically get values of a particular type. Now, the introduction rule for the unit type is very simple because, I mean, the unit type, we know we're really trying to model a terminal object here. In terms of set theory, we can think that this really just represents a set with one element. And so as a type, if we're thinking kind of set theoretically, we'd expect that this type 1 here has a value star, okay? And that would be true in any scenario. So this is the sort of formalization of this. It says that in any context gamma, we have that star is of type 1. Okay, and notice this horizontal line with nothing above it. That means that in any scenario where we have a context, we can say that that entails that we have this value star of the unit type. In other words, in terms of set theory, we can always grab this value star of type 1. We don't have to do any kind of special tricks to point to it or construct it or anything. It's always there. We always have this single element of type 1. So in terms of logic, this kind of unit type corresponds to a sort of true proposition, the proposition which is always true. And so what this means in terms of logic is that in any context, we'll always have this proof star that true is true. Okay, so it's this kind of trivial idea that true is always true, and we always have this sort of thing that we call star, which we can think of as a proof of that elementary notion. In terms of set theory, what this is basically saying, well, we can think of it as saying we can always produce a value star of type 1. But let's look at a specific example. So let's take gamma here to be this value x of type A. So this is a special case of this. And in this case, if we think about this set theoretically, what this is telling us is that we have a kind of function from A to 1. And what this function is doing is it's sending every sort of general value x of type A to star. So what is this function? Well, it's our old friend exclamation mark A, the unique function from this set A to the singleton set 1 that kind of sends all the elements of A to star. Okay, so we're seeing that we're getting these kind of familiar ideas from category theory / set theory emerging just from these kind of rules of type theory. Now, so far we've only just started talking about the unit type, but we'll go on and talk about all sorts of different types and really see that we get this amazing theory that can handle all of the stuff going on in Bicartesian closed categories. So the idea is that as we go through these different types, we're going to look at the sort of typing rules for them, how to introduce values of those types and how to use them. And then later we're going to look at the sort of equational theory, which tells us how these things that we can make and use can be considered equal to each other. And that's sort of the final piece of the puzzle as far as how the type theory works. So we're going to talk about the product. So remember, if we have types A and B, we can form this type A times B. And the first thing is, how do we get a value of type A times B? And to do that, we use the so-called introduction rule for the products. Okay, so an introduction rule tells you how to form values of a particular type. And this rule is quite straightforward. It says that if we have a context gamma where we have a value A of type capital A and a value B of type capital B, then in that context we have this pair A comma B, which has a type A times B. All right, so there's different ways we can think of this rule. In terms of set theory, it's quite straightforward. If we have a member of set A and a member of set B, like drawn here, then we have this sort of pair A comma B, and that's going to be a member of this Cartesian product of these sets, which is A times B, the set of all pairs of a member of A and a member of B. The logical interpretation of this is also really quite interesting, because if we're thinking in terms of logic, then capital A would be a proposition and capital B would be a proposition, and this A times B here, this product, this will correspond to the proposition A and B. And what this says in that context is that if little a is a proof of proposition capital A and little b is a proof of proposition capital B, then we have little a comma little b, and that's a proof of the proposition A and B. All right, so if I claim that 4 is even and that 6 is a multiple of 3, and I have proofs of those two things, and I sort of pair those proofs together, then they constitute a proof that 4 is even and 6 is a multiple of 3. It's this idea of sort of combining proofs of individual propositions to give a proof of kind of many propositions at the same time. Yes. So let's have a look at how we can use this. So the idea of this rule is that if for any context we can form these two things, we can form this. And so it's a good idea to think about these kind of things as a sort of tree structure. Okay, so we can sort of visualize this a little bit like this, okay? If we can form a structure like this, and we can form a structure like this, then together they can give us a structure like this, okay? So think about these drawn like this, for example. So here's an example where we take this context here to be that z is a variable of type h. And so let's try and interpret this sort of visually, okay? So what we're saying here is that we have this term little a of type capital A, which may involve this variable z of type h. So we can think that that's sort of specifying an arrow a from capital H to capital A, because we're sort of saying that our value a is depending on this value in h. Now, you may say, oh, that's not really an arrow, that's just a term which might have a variable z. And that's actually correct. There is a way to think about this as an arrow slash function, and to basically interpret it as something like this. But at the moment, this correspondence is a little bit fuzzy, and it will become clearer when we get to talking about function types. Okay, but for now, I'm being a little bit fuzzy about the sort of ways to illustrate these rules graphically. I mean, at the end of the day, you can talk about how to interpret these kind of type theory rules, but the real important thing is what the rules are and how they play with each other. Anyway, we take this rule here, the product introduction rule, and we're looking at the case where gamma is z of type h. So this becomes this here is this, so this is saying that we have this variable b that may depend, so this is saying that we have this term b, which may depend on a variable z of type h. And what this rule is saying is that given these two things, we can form this new term a comma b, which is a term of type a times b, and it may again depend on these values z from h. So again, we can almost think of it like a function. So this is really similar to the idea we have. So this is kind of corresponding with this idea we have when we're forming products in category theory, that if we have an arrow from h to a and we have an arrow from h to b, we can form this kind of pair arrow from h to a times b. And this is sort of how we introduce values of this product type. Okay, so that's kind of how we can form values of this product type. The other thing is, how can we use those values? And the way that we use values of a particular type are by using these things called elimination rules or destructors. And the idea of these basically is they allow us to take a value of a particular type and then sort of transform it into something, ideally something more familiar. So this first product elimination rule lets us take a value p of type a times b and basically do a projection on it to get a value of type a. So formally it says that in any context gamma, if we have that p is a value of type a times b, then that implies that in that context gamma, we have that doing fst on p gives us a value of type a. Now, This FST thing here, we can really think of it as the first projection. Okay, it takes a pair and it just returns the first entry in that pair. But the critical thing is that in type theory, as we're setting it up, you're seeing this for the first time and you don't really know what it means. You just know that if we have a term like this, we can form a term like this. And this is all the rules that we have so far. And later we're going to get some equations, and then you'll be able to make sense of this as a first projection. So the point is that this whole theory is sort of self-contained within the symbols. So in a sense, you don't need to take in anything apart from the actual rules, which a computer would take in. And you can sort of see how the rules interact and later understand why this does indeed correspond to the first projection. I mean, all this rule is really saying so far is that if we have a context where we have a value p of type A times b, then we always have this value fst of p of type A. We haven't yet said anything about how this thing works, but we will later. And I'm telling you that really this fst thing here corresponds to this kind of first projection from A times b to A, which is selecting the first entry of our pair. But we'll see that later. So let's have a look at a special kind of application of this. Let's pick the case where gamma here is just p of type A times b. So that's a case of this. And so now we can do our first little proof in type theory. And it's basically the construction here of this kind of FST function, this first projection function. And so the idea is that we start with nothing, and then we use our kind of case idea, which, if you recall, says that if we have a context, a list of type declarations, then those entail any particular member of that list. So, for example, this entails itself. Sometimes this is just called the identity rule, because you can see it actually corresponds to an identity function as well. And so we get that from nothing. And then if we apply this product elimination rule 1 here, with this context gamma being p in A times b, since having p in A times b entails that we have p in A times b, we can use this rule to get that having p of type A times b entails that we have fst of p of type A. And if you think about what this is in terms of set theory, it's really giving us a function. It's saying that here we have this term of type A that depends on this value p of type A times b. So this is really defining for us this kind of function, this sort of first projection function. And in a similar way, we have this second product elimination rule, which is saying that if in a context, if we have p of type A times b, then in that context we have second of p of type b. So this is giving us our second projection. And so you see that what we've essentially done is describe the product and describe these special kind of arrows associated with it. Now, we still need to do some kind of work with equations. We want to, for example, prove that this diagram commutes and prove that the universal property is satisfied. But we'll get onto that later. The important thing for now is that we have this product type and we know how to introduce values of that type, and we know how to use / eliminate those values using these projections here. And then in terms of logic, what does this mean? Well, it means that if in a context gamma you have a proof P of A and B, then in that context gamma you have this proof FST of P of A. So if A and B are true, then A is true. Okay, it's this kind of idea. Okay, so now let's talk about function types. So these correspond to exponential objects. So when we write A arrow B, that denotes a type, and we can think of it in terms of set theory as the type of functions from A to B, or we can think of it in terms of logic as the proposition that A implies B, or we can think of it in terms of category theory as this exponential object, which we often write as B to the power of A. Now, I like function objects a lot. For one thing, thinking about them brings lots of other aspects of type theory into focus. I mean, another phrase for this kind of simple type theory is lambda calculus with sums. Well, lambda calculus is all about the kind of lambda abstraction, which is all about this kind of way to form functions that we can then play with to do computations and things. And that's really a lot to do with function types. Now, another thing I really like about function types is that thinking about them allows us to understand a lot of what the other things mean in type theory. Like, at the end of the day, type theory is just a sort of system for manipulating symbols, and the meaning of those symbols is really given to us by the way that these different rules of type theory interact with each other. And when we know how exponential objects work, and when we know how function types work, it really sheds a lot of light on how these different expressions can be interpreted as arrows in categories, and how things like substitution work. So the idea then is that if we have types A and B, then we can write A arrow B, and that's the so-called function type. Okay, and the reason it's called that is because in set theory this will correspond to the set of functions from A to B. And so there is an introduction rule which allows us to get values of this type, and this is the function introduction rule. Okay, so each of these rules, sometimes called an inference rule, has a sort of horizontal line, and it basically tells us that if we have something like that, then we can form something like this. And notice also that these things could easily be implemented in a computer. Okay, we could write these, for example, a context would just be a list of type declarations, so we could spot it just by, it would be a list of symbols like this, and we could easily write some kind of a program to check whether a given input has this sort of form. However it is we're storing these type declarations, we could check, well, is this thing a list of type declarations? Is this thing a context? And if we detect such a thing and we have a type declaration on the end and we have that this entails a term, then we could apply a kind of rewrite operation or something and generate this judgment at the bottom. And all of type theory can be done by stringing together these kind of judgments to make these sort of proof trees or whatever you want to call them. And they can basically be implemented in a computer by doing a load of rewrite operations, one for each of our inference rules. So anyway, we have this function introduction rule. Now, there's something a bit different going on here, because what we're basically saying here is that if we have this situation where in some context we have a variable x of type A, and that entails that we have this term B, well then in that situation this context gamma entails that we have this function from A to B. And notice how we're writing this. We're writing lambda x of type B dot B is of this type. Now this is something a bit new, because up here this x here is a variable, so x might appear in this term B as a sort of free variable. It's a variable and it's free to take any values we want, and we can just treat it like a normal variable. But what we do here is we sort of put this lambda x on the front of our B, and what we're really saying there is that now this x is sort of bound to this B by this kind of lambda, and that now we've really got a kind of function where we're ready to take in this value x of type B and return this value little b of type capital B. And that's what gives us our function from A to B. So we'd say that this variable x, which may appear in this term B here, is bound to it by this sort of lambda abstraction. So it's similar if you've done calculus, when you write something like this, you're really saying that this sort of x here is bound by this kind of integration construct, because it's no longer a sort of variable that we can freely assign values to. It's sort of set up like this. So if we have a y in here, like that, we could choose the value of that y, and that's a free variable, but this x here is actually bound inside this kind of integration. And in a similar way, this x here is bound. So when we write, for example, that we'll do lambda of x of type integer dot x plus 1, and I mean numerical addition there, what we're really saying here is that we've got this function from n to m, from natural numbers to natural numbers, which takes in a value and adds 1 to it. So this is our function introduction rule. And let's have a look at how this works. So we'll do an example where this context gamma is empty. And so here's the example. And what it's really doing is it's giving us another perspective on the meaning of this sort of notation. Because I said we can think of this as meaning that we have a function from a to b. So we have the value little b, a term, which might have this variable x of type a, which it depends on. And we can see that by doing this function introduction rule, we can make this explicit, and we can think, well, actually, yes, we have this function. It takes in a value x and it returns b. And so when we think of how to represent this, we may like to represent it like this, to just say that this term b here gives us a sort of arrow from a to b. Or we might want to think of it like this, that it takes in a value x and it returns a value b, and it's really a function from a to b. So I like to be a bit flexible with how to illustrate these things, because the type theory itself is quite flexible in the sense that there's many ways to interpret things. But essentially what this is doing is it's letting us think of this kind of function here from a to b as a value of the function type, which makes good sense. So basically, in terms of set theory, you can think that this function rule allows us to take this term, which may have a variable x of type a, and really think of this term as defining this function from a to b. Now, the meaning of this, how it evaluates and how to use this function and so on and so forth, is something that we're going to see as we unroll the rest of our theory. But I think you probably get the idea that it's basically just forming this function from a to b. Also, in terms of logic, this makes good sense, because what it's saying is that if in a context gamma we have a proof x of proposition A, and we know that that entails that we have this proof little b of proposition capital B, then what this is telling us is that in this context gamma we have this proof that A implies B. All right, if I know that when I have evidence of A, I can get evidence of B, then I have evidence that A implies B. It makes sense. And the real idea behind these function types is that we're really representing things that are going on with exponential objects, okay? So this really we can think of as meaning the exponential object, b to the power of a. And so if we look at another example of this function introduction rule, and this time we're going to let gamma be this context z of type h. So if we write that out, we get this rule here. And what this is telling us is that if we have a term b, which might depend on a value of h and a value of a, so we can think of that as a sort of arrow from h times a to b, because it takes in these two values, a value from h and a value from a, and returns a value from b. So this is defining our sort of function from a product to another object. And then one of the things about exponential objects is that there's this notion of sort of currying or transposing this. So we can convert an arrow of this kind of form to an arrow like this, an arrow from h to b to the power of a. And we typically call an arrow like this b bar, the transpose of b. And you see that this is really what our function introduction rule is doing for us, because if we apply it, we see that given an expression like this, as in given an arrow like this, we can form an arrow like this, which corresponds in type theory to saying that we have this function which is going to take in a value x of type A and return a b. That's going to be a function from A to B, and it may depend on this value z of type H. So b bar here, this thing is really telling us that we have this value of type A arrow b, or we write it as b to the power of A, it's just another notation for the same thing, and it may depend on this value z of type H. So this is really formalizing our idea of transposition. So okay, that's function introduction. That's how we can make a function, essentially. The other big idea with function types is that we can use them, okay? So this is called the elimination rule for function types. It tells you how to use a value of a function type. And really for us, it's just telling us what this idea is of actually evaluating functions on inputs. So here's the rule. It says, if in a context gamma, we have a function f from A to B, and also we have a value little a of type capital A, then in the same context gamma, we have this value f of A of type B. So notice we write the f, and then we put the input in brackets. And since the f maps A to B, and the little a is of type A, f of A is of type B. Okay, so this is sort of formalizing, at least type-wise, how function evaluation works. And so there are many different ways we can think about what this rule means. Of course, in terms of set theory, this means if you have a function from A to B and you have a value of A, you can operate the function on the value and get this value f of A of the set B. In terms of logic, what this means is if you have a proof f that A implies B, and you have a proof that A is true, then you can get this proof that B is true. Okay, if A implies B and A is true, then B is true. And also we can interpret this sort of in terms of category theory. So we really want to get at this evaluation arrow. I mean, one of our goals in unrolling this theory is to show that it really does correspond to a kind of theory of Bicartesian closed categories. So we want to show how we can kind of get at all of this fundamental category theory machinery. So I've already talked about how we can basically transpose arrows, transposing this to get this. And we can use this rule here to get at this kind of evaluation arrow, which basically we can think of it as it takes a function from A to B and an input A, and it returns a value of type B. So we can really derive a sort of expression for this kind of evaluation arrow like this. So let's think about the situation where we have this context here. We have this G, which is sort of a function type from A to B, and we also have this value x of type A. Now, given that, we can use our kind of case rule to get that this entails that we have this G of type A arrow B. And also we can use case again to know that in this context, this entails that we have this value x of type A. And so now if we use these two ideas, which notice we can get them from nothing, hence the horizontal lines with nothing above, but once we've got these two things, we can use this function elimination rule here to give us that in this context, where we have our function g from A to B and our value x of type A, we have this g of x of type B. So look at this bottom expression. And thinking about this as a function, we can think, well, it takes in a function from A to B, and it takes in a value x of type A, and it returns a value g of x of type B. So this is really our evaluation arrow associated with our exponential objects. So it's really worth thinking about this. I'd say that exponential objects are one of the most sort of interesting ideas in category theory, and really the deeper you go into them, the more you learn. And yeah, they're very, very interesting. So it's really useful to have this kind of type theoretic perspective on it. I mean, it's no coincidence how important lambda calculus is for things like the foundations of theoretical computer science. These are really important notions. Okay, so we can use these function types to really understand what our kind of fundamental notation means. I've kept saying so far that we can think of this kind of notation as meaning that we have a sort of arrow B from H times A to capital B, okay, because we have this term little b here, which may depend on this variable z of type H and this variable x of type A. But we can really see now sort of why I say that, because we can see that we have these sort of three different ways of thinking about the same thing. Now, it's an analogous situation if we have more variables, more inputs. But I'll focus on the case with two inputs because it's interesting to actually see how we are able to show this kind of thing formally. All right, so basically what I want to do is to show that these three different kinds of expressions are all sort of equivalent. I mean, I'm not actually going to go as far as showing things are equivalent. I'm not really talking about anything being equal at the moment. I can talk about that later. Once we have a kind of equational theory, but I at least want to show that with the kind of typing rules we've got so far, we can convert between these three different forms. And I tell you that these are really just three different ways of sort of saying the same thing. So the first one is that we have this term little b of type capital B, which has a variable z of type H and a variable x of type A. That's one way of saying it. Another way of saying it, this is a kind of purely functional way, is that we have a function which sends a value of H to a function from A to B. Okay, and then the third way of saying it is that we have a function which takes in a pair of a value of H and a value of A and returns a value of B. And these are all interchangeable. Now, the rest of this board is sort of trying to prove that. And I'd like to emphasize here that the point is hopefully to clarify, how we can get at these things formally. But if this is like too much to swallow on a first exposure to type theory, then you don't need to pay too much attention on a first viewing. But as you get into it, you'll probably be quite interested in how can we formally do things? So, okay, how can we do this then? How can we convert from an expression like this to this? Well, this is our sort of first part of our exposition here. So we'll bring along this context gamma, which could be a general context. We'll bring it along for the ride, but in this kind of situation, we can just think of our context gamma as being empty. So we start here with this assumption that given a variable z of type H and a variable x of type A, we have this term b of type capital B. Now we do our function introduction rule, and that sort of wraps this x in a lambda abstraction. And then we just do function introduction again. And so now in our context gamma, we have this function here from H to the type of functions from A to B. And so basically the way this function works is it's ready to take in a z of type H. Once that's supplied, we have this function from A to B here, which is ready to take in an x of type A and return this term b of type capital B. When I write this sort of thing, I have this lambda here, and then we record the type of the variable that this lambda is using. But sometimes for shorthand, we just don't bother recording the type. So that kind of notation is fine too. So that's basically how we go from this form to this form. How do we go from this form to this other one here? Well, that's a bit more complicated, and it's laid out here. So when we write this context, weakening gives us that this entails that we have this value p of type H times A, and then we can do the first elimination rule for the product to have that when we have a context gamma and we have a term P of type H times A, then we have that doing the first projection on P gives us this value of type H. So that's that far. Going this way, well, we're assuming that we have this in our context gamma, we have this function K, which sends H to a function from A to B. And so we can do weakening by adding in this variable P of type H times A. And now we can apply the function elimination rule, okay? Because we have a function here that takes in a value of H and we have a value of H here. So we can get that in the context of gamma with this variable P of type H times A, we have that K of first of P is going to be a function from A to B, because that's there. And now over here, again, we can introduce this context. And then in a similar way to over here, we can get that given this context gamma and this variable P of type A times B, I made a mistake here. This is supposed to say H times A. So we have this term P of type H times A, and then doing the second projection on it gives us something of type A. So now we can do function elimination again. We have a function from A to B. We have a value here of type A, so we can apply this function to this, and we get that in this context gamma with this variable P of type H times A, we have that doing K on Fs on the first projection of P gives us this function from A to B, and doing that function on this input in A gives us a value of type B. So we've gone from this kind of expression to this kind of expression. And now we can complete the circuit to go back to our original expression. So this is the third part of our demonstration here. So we're assuming now that in our context gamma with a variable P of type H times A, we have this term beta of type B. Now, using function introduction, we can now get that in this context gamma, we have this function that's ready to take in a value P of type H times A and return a value of B. And now let's get something ready for that. So we have that given this context gamma and a value Z of type H and a value X of type A, we have this value Z of type H. Similarly, given gamma, Z and X, we have X. And so we can use product introduction to get for the given gamma, Z and X, we have Z comma X, which is of type H times A. And that's the right type to be an input for this kind of function here, which we can get by taking this, we can get to this line by taking this and doing weakening to introduce a Z and H. So then we can do function elimination to apply this function to this input. And we have what we wanted, that given gamma and given Z of type H and given X of type A, we have this term here of type B. So we've got back from here to here and sort of shown that all these three different forms are at least interchangeable. And with the rest of the kind of equational theory that we're going to encounter later, it can be shown that these are all really three just different equivalent ways of talking about the same thing. So it's wonderful to have all this and to know how many different sorts of interpretations there are of this type of thing in terms of set theory or logic or any other kind of Bicartesian closed category. Okay, so these are the final typing rules that we need. So this first one is about this empty type. Now, the idea of the empty type is, of course, it's empty. So there's no introduction rule for it. There's no way to introduce a value of it. But a bit peculiarly, there is a way to sort of use values of the empty type, even though there aren't any. And that's called the elimination rule for the empty type. And what it says is that in any context, if we have a value E of the empty type, and we have any type A, then we can produce a value of type A called abort A of E. And this is really sort of encapsulating this idea that there's a sort of function with no inputs from the empty type to any other type. We can see that by looking at a special case of this where the context gamma is just E of type 0. So Then from case, we get that E of type 0 entails E of type 0, and then applying this empty elimination rule gives us this function here, really, which takes in a value E of type 0 and returns this value of type A. So that's defining our kind of abort function. That's sort of how to think of this in terms of set theory. It's kind of talking about a function with no inputs. In terms of logic, this is the very interesting idea that basically from false, anything else follows. Okay, so what this is saying is that in any context, if you have a proof of the false proposition, then you can get a proof of any other proposition A. So it's kind of like if in arithmetic you assume that 1 equals 0, then you can use arithmetic to prove anything else you want about arithmetic, like that 7 equals 9 or whatever. So that's the first one. The other ideas are about sum types. Okay, so sum types, basically, I always like to think set theoretically to start with. So if you have a set A and a set B, if you sort of tag the values of set A by writing in L on the front of them, so in L of 1 and in L of 2, and if you take the values in set B and put in R in front of them and gather all of those together, that's the set A plus B. So it's the disjoint or tagged union of these sets. You tag these ones with in L and these ones with in R and gather them together, and that's the sum of A and B, also known as coproduct, right? So a bit more formally then, we have a way of introducing values of this sum type. So if we have, in our context gamma, we have a value A of type A, then we can get this value in L of A, which is of type A plus B. So this is sort of giving this idea of this kind of injection function, injecting these values of A into this sum type. And we can look at a special case of this rule where gamma just consists of saying we have this value A of type A. And then, of course, in this case, this is a variable, and our case just gives us that this holds automatically. And then we see that we're really sort of defining a function from A to A plus B, which is this left injection function. In a similar way, there's another introduction rule for the sum type, which allows us to take a value B of type B and produce the right injection of B. So that's giving us our right injection function. And we also have this sort of way of producing the sort of coproductive pair of two arrows. So this is the sum elimination rule. So this is telling us how we can actually use a value of the sum type. And the basic idea, sort of roughly speaking, is if we have an arrow from A to C and an arrow from B to C, or let's think in terms of functions. So if we have a function from A to C and a function from B to C, we can form a function from A plus B to C, which operates like U does here on the values that came from A, and operates like V does here on the values that came from B, and we call such a function match. So that's basically what this rule is saying. I should also just mention, I forgot to say, in terms of logic, how can we think of this sum introduction rule? Well, we can think that it basically says that if in a context of gamma we have that A is true, then we have that A or B is true. Okay, so in terms of logic, the empty type is false and A plus B means A or B. All right, so this is meaning A or B. So obviously, if I can prove that A is true, then I'm proving that A or B is true. If I'm a man, then I am a man or a woman, right? It makes sense. Okay, so we've talked about these introduction rules. What about this elimination rule here? Well, we can make some sense of it if we just sort of ignore the context, okay? So then it's basically saying if we have a value S of type A plus B, and we have this kind of thing, which is really saying we have a value U of type C that might depend on a value X of type A. So we can think of this as sort of like a function from A to C. And similarly, we can think of this as sort of like a function from B to C. And then given all this, we can find this term of type C. All right, so this is a bit funny notation. This is actually a dot here, and this means something new. So in type theory, when we write these kind of expressions, we like to record all of the different things that our things vary on. That's why we write this sort of subscript A plus B, so that if we're implementing this in a computer, we're not going to get confused between this and some other left injection associated with some other coproduct. And in a similar way, when we write this match function here, we really mean this sort of intermediary arrow here from the coproduct to the target object. And you see here it's called match, and this is the input, this is the S, this is the value of A plus B that we're sort of mapping. And then this here says that this depends on this value U of type C, or term, and this notation here means that this depends on this term U of type C, but also that U has this variable X of type A. Okay, so it's a kind of variable term kind of way of recording this sort of function here from A to C. And it's really very similar to the sort of lambda notation that we were using before, in the sense that you can think that this is really binding this variable X to this U here in this expression, in the sense that we're really thinking that this X here is now bound. And in a similar way, this V here depends on this Y. And so we need this information and our inputs, and then this match will work appropriately. We can't really see that yet. We need to get onto the equational theory of these coproducts later. But I'm telling you that the way this is defined is that basically we can think of this as a sort of function from A plus B to C that works like this sort of function U does on values that came from A, and like this sort of function that V does on values that came from B. So it's basically similar to the sort of, okay, this is a bit of an abusive notation, but we can almost think it means a similar thing to this sort of notation does that we saw before, and when we were talking about coproducts. Okay, so we're just about to get on to this sort of equational part of this simple type theory. But just before we do, there are these sort of 3 extra kind of structural rules here. Now, the truth is that we don't really use these rules at all during this video. And so I'm just going to kind of gloss over them. You can read them for yourself. I mean, gamma and delta here are contexts. This means joining together those with this type declaration that X is of type A. You can read all of this stuff yourself and think about how to interpret these rules in terms of category theory. These are common sort of structural rules about how to manipulate these kind of contexts and things, which also appear in logic. However, they don't seem to be used very much in the approach to simple type theory that I'm taking. The only thing I should explain is what this notation means, because we're going to be coming across this quite a lot. So notice, if we look above the line, we have this term A of type capital A, and also this variable X of type capital A. Now what this notation means is that we take this term B and we replace all of the free occurrences of X, as in the ones that aren't bound to lambda operators and things. We replace each of those X's with this term A. All right, so it's this idea of replacing a variable with something specific. Now, there's a bit of a caveat here that I'm not going to make a big deal of here. I mean, I am linking in the description to a document I wrote which goes through this type theory in much more sort of careful detail. But I will say that whenever we have these kind of inference rules which involve doing this sort of substitution, like this is really saying we generate this term B by substituting every free occurrence of X with this term A. Well, whenever we have such a rule involving substitution, I think we can only really do it in a special case. All right, so this is probably going to sound technical and cryptic, and if this is your first exposure to type theory, then ignore this, but I'll just say it quickly. So if no free variables of A become bound in this term after we do the substitution, then we say that A is free for X in B. And we can only do this kind of thing if that is the case where A is free for X in B. And that kind of condition holds whenever we have these kind of rules involving substitution. It doesn't matter here because we're just replacing one variable with another, but there are other cases which involve substitution, and if you don't want to get yourself tied in logical knots, you've got to watch out for these kind of bound variables. So yes, I wanted to briefly mention these other structural rules. You can check out this book on the practical foundations of mathematics, chapter 2, talks about these things more thoroughly. But like I say, I'm not really going to use them. Now I want to start to introduce this equational theory. And it's using this that we're really going to make sense of the things we've defined so far. So the important terminology is this, that in this context gamma, we have that A is identical to A dash. And what this notation means is that we have these values A and A dash of type capital A, and we're considering them to be equal. Okay, so this triple bar notation is sometimes pronounced as is equivalent to. I shall just say is equal to. Okay, so the idea here is that we're talking about equality within the theory. I mean, equality in general in type theory is a fairly subtle business. Because what do you mean when you say things are equal? Are you defining them to be equal, or are they sort of being shown to be equal by using the theory? Now, the idea here basically is that we're sort of declaring these things as equal, and we have some rules for how this works. So essentially, just as we are sort of using our type theory rules and things to show that we have these values of different types, we also have rules for when we're able to generate statements saying that things are equal. So we're going to use our kind of type theory rules to arrive at these kind of results. But in order to do this, we have various sorts of equational rules, which are telling us kind of in the scenarios where our types are playing, when are the values involved going to be equal. But kind of before we sort of get going, we want to encode the basic kind of features of equality. Okay, so I'll just say for those that know, this is basically encoding the idea that we have this equality is really a kind of equivalence relation. So more specifically, we're showing that equality has sort of three properties. One of them is that it's reflexive. Okay, so this first rule here, it says that in any context gamma, if we have a value A, then in that context we always have that A is equal to A. Every element is equal to itself. Okay, we also have this idea of symmetry. So this is obvious kind of what this means in terms of set theory. If you want to think of it in terms of logic, you could think that we're sort of equating proofs. Okay, so when is one proof of proposition A considered the same as another proof of proposition A? All right, so our first condition is reflexivity. Every element is equal to itself. Our second condition is symmetry. If A is equal to A dash, then A dash is equal to A. And finally, transitivity. If A is equal to A dash and A dash is equal to A double dash, then A is equal to A double dash. And I urge you, if you're new to this kind of thing, try and make a proof tree to show that if A equals B and B equals C and C equals D, then A equals D. That's just going to be using this transitivity rule repeatedly. Let me add this final rule here because I think it's kind of useful. What it says is that if we have a context gamma, and in that context we have these values A and A dash of type capital A and they're equal, then we obviously get that in that context this value A is of type capital A. Okay, so now we're getting really into the equational sort of theory of these things. So the basic idea is that associated with these different values of different types that we can generate, there are various sorts of equality. And so let's start by considering the unit type. So think about how you might explain to someone what a set with a single element is. You would probably say something like, well, you could say something like, well, there's an element in this set and it's called star, and any element in this set is equal to star. And so we've already encountered this idea that there's this element of type 1 called star, and we now also have this so-called uniqueness principle for the unit type, which basically tells us that in any context gamma, if we have this value v of type 1, then we can get that value v is equal to star. In other words, the only value of type 1 is equal to star. Okay, and we can use this. So let's consider a special case of applying this equational rule when gamma is x of type A. So in this case, we have that having x of type A gives us this value v of type 1. So you can think of this as sort of giving us a function from A to 1. And then what this is essentially saying is that this function is equal to this function that sends everything to star. And that's exclamation mark A. So you see here that we're really getting the kind of universal property of a terminal object, that there's exactly one arrow into it from any object. So the introduction rule for the unit type gave us the kind of presence of an arrow from any type to the unit type. But now we also have this way of proving that any sort of arrow from A to 1 is actually equal to this exclamation mark A arrow that's like the function that sends everything to star. So this is well worth thinking about. And we also have rules which are telling us how the product works, okay? And so we start with this product computation rule 1. And what this is saying is that if we have a value of type, and what this is saying is that if we have a value of type A and a value of type B, then it's always true that if we form this pair, A comma B, and then we do the first projection on that pair, that returns A. So this is sort of obvious. So it's sort of obvious that things should be like this from a kind of computational view. I mean, of course, if we form this pair AB and then we want to take the first one, we're going to get A. From a sort of category theory point of view, this is really telling us that this sort of diagram, well, the bottom part of this diagram commutes, okay? That if we form A comma B and then we do the first projection on that, that gives A. And if we want to think about this sort of in terms of functions, we can consider the case where gamma here is just consisting of declaring this variable z of type h, and then we can think of these a's and b's and a comma b as functions from h, if we like. And so again, if you recall the sort of definition, the categorical definition of a product, one of the stipulations is that when we have an arrow A from H to capital A and an arrow B from H to capital B, then there has to be this unique arrow A comma B, which makes this diagram commute in the sense that if we do the first projection after this, we get this, and if we do the second projection after this, we get this. Now we get the presence of such a pair arrow, we get that it has the required features as a consequence of our product computation rules 1 and 2. And then one still has to show the uniqueness of this arrow. And basically the way you can do that is by using this product uniqueness principle here. So what this uniqueness principle is saying is that if in any context gamma we have a term P of type A times B, then we can always write P as the pair of what we get if we do the first projection on P paired with what we get if we do the second projection on P. And once again, if we want to think about this in the context of these sort of diagrams, as if we have a sort of arrow P like this, we can consider using this rule in the scenario where gamma here just says Z is of type H. Anyway, it turns out that you can use this rule to basically show that if P also sort of has the property that doing first after it gives A and doing second after it gives B, then we must have that P is equal to A comma B. So that's essentially proving the kind of universal property of the product, and essentially it's sort of showing us that having these kind of type rules is enough for us to be sure that the product kind of thing that we're defining here acts like the sort of categorical product that we want, because that's what we want, because we're trying to emulate what's going on in the theory of Bicartesian closed categories. So if you want to look at that, I mean, there's various sort of extra details that I'm going into in this sort of document that I'm linking in the description, I mean, I really just want to give you the kind of core rules so that you can explore this theory. So I'm really focusing on explaining what exactly the inference rules are behind this theory. Okay, so now we've got to the equational theory for function types. And one of the main things that this tells us is how we can sort of use functions and how they work, really explaining this idea of the lambda abstraction. So let me start by explaining the main idea roughly. Think about arithmetic. Think about this expression, x plus 1, where we're having a number and we're adding 1 to it. We can represent this in terms of a lambda abstraction like this. We'll take an x, which is a natural number. We'll do lambda of it and then we'll put a dot there. Now we have a function from numbers to numbers. It takes in a number and it returns 1 plus that number. So if we want to operate this with an input, so let's say 6, the way we do it is we take this term here, so that would be x plus 1, and we get that term and we replace the x with our input. So we replace each x with a 6, and that gives us 6 plus 1, which is going to be our output. Okay, so that's kind of how this lambda idea works. And this is the idea formalized by our computation rule for the function type. So basically what this is saying is that if in a context gamma we have this term b, which might involve this variable x, of course we can turn that into a function, and also if we have a term little a of type capital A, well, if we turn this into a function and use a as the input, then the result is what we get if we take this term little b and then we replace each instance of x with a. And of course, in order to be able to do this, we need that a must be free for x in b. So there's various things that we can get out of this idea of how function computation works. One of them is this kind of idea about how function composition works. So let's say we have a function a from q to capital A. Well, we might encode it like this. We'd say that the term little a of type capital A has this variable q of type capital Q. And maybe we also have a function b from capital A to capital B, encoded like this. So the term little b might depend on this variable x of type A. So we have these two kind of functions that we're representing like this, and we want to compose them together. So if we take this and we do some weakening, we can introduce a q into the context. And now we have two things that we can apply our function computation rule to. So we can sort of apply this function here with this as our kind of input. And what this gives us is that when we have this Q of type capital Q, then that entails that we have that doing this, like we form this function with our B, and it takes this value x and it returns B, but for that value x we're going to use this A. And then by this rule we know that this result is going to be what happens if we take this term B and replace the x with A. And think about what that means. We have this kind of function B here from A to B, but the way it sort of works on A is it has this variable x of type A, which it depends on. But if we replace that variable x with this kind of term A here, then that's kind of like composing the arrows, right? Like, because I'm replacing each of the values x that this B should operate on with the value A of little q. So the result is going to be B of A of little q, which is really this composition. So this resulting function here, this composition, can be thought of as depending on a variable little q of type capital Q. And it takes that variable and then it forms this term A, which might depend on that little q, and then it uses that as the sort of input for this next function here, which replaces all of the x's in B with this A, and that gives us this resulting kind of composition. So this is how we can think about sort of function composition, or more generally arrow composition, in these sort of in this simple type theory. Another thing that we can get from this rule is a sort of demonstration that this kind of triangle associated with our exponential objects really commutes. So remember that b to the power of a, in type theory we write that as the type a arrow b, the, if you like, the type of functions from a to b. And we can sort of see that this triangle commutes. It's a bit rough at this level because I'm trying not to get into so many details now. If you really want to dig into this stuff and see, for example, a proof that we really do have an exponential object in this setup, you can dig into that document linked to in the description. But just to see the rough idea, consider using this rule here where for our context we use z of type h comma x. We use z of type h comma x of type a. Well, that gives that this and this imply this line here. But we can start off with this line here for our sort of starting assumption. So we start by assuming that this term b of type capital B depends on this value z of type h and this value x of type a. So that's really defining this arrow here. And then we sort of want to try and show that this triangle commutes. So if we do weakening, we can introduce an x of type a on the left here. And then if we apply this function computation rule, then we have that in this context, we have that this left-hand side equals the right-hand side. We have that this equals this. So this is the same as this because we're just replacing. So we have that this expression here is equal to this one, where our replacement here is just replacing x with x, so it just leaves b alone. So what this is basically saying is that this b here is equal to this thing here. And here lambda x dot b, we can really think of that as this kind of arrow from h to b to the power of a. And then when we sort of do the evaluation on that, we're going to be operating this kind of function that we formed on the x in here, and we see that that gives the same result as our b here. So this is part of the story. There's more to the story of how these kind of function types work. I mean, in terms of category theory, we don't just want to show that this triangle commutes, we want to show that b bar is the only arrow from h to b to the power of a, which makes this kind of diagram commute. And we can do that, I'm not going to go into it here, but we can do that using this other kind of important equational rule here that we have, which is called function uniqueness. So what this is basically telling us is a way we can always kind of represent a function. So suppose we have, in a context gamma, we have this f, which is of type a arrow b. So it's basically like a function from a to b. Well, the idea is essentially that we can always represent it in this kind of lambda form. Okay, so basically, if we have an x which is not a free variable of f, then we can always write that f is equal to this kind of function. So it's lambda x dot f of x. So we can basically, if we have a function from a to b, we can sort of think about what happens when we operate that on an x. And that'll give us a value of b, and then we can use a lambda to sort of remake it back into a function again. So it's ready to take a value x and return f of x. And the idea is that building that up will give us something equal to our original f. And so that's the uniqueness principle for the function type. And then we want some other sorts of what should be kind of obvious ideas. So we want this kind of rule here, which basically says doing a particular function on two equal inputs will give equal outputs. And this rule here, which basically says that if we have two terms b and b dash which are equal and both depend on a value x of type a, then when we make them into functions by doing this kind of lambda abstraction thing here, those two functions will be equal. And there's another idea which I'm not going to go into here, but it's pretty straightforward really. The idea is just that it sort of doesn't matter what we name our variables, if that makes sense. So then the final kind of thing is this idea basically that if we do a so-called alpha conversion between two of these kind of expressions with bound variables, and if we just sort of rename the bound variables, that doesn't really change the nature of the function. So I'm expressing this roughly here. So the idea is something like if we have a term b and then replacing, say, all of the variables x with y turns that into another term b dash, then lambda of y dot b dash should give the same function as lambda x dot b. In other words, just renaming the bound variables basically gives us the same function. And there's another kind of version of that for the match term, which is a similar sort of expression with bound variables that we see appearing for the sum type. So I'm sort of rushing through this. I think I'm touching on all the rules here, but I'm kind of glazing over some of the details. So like if you really want to know, for example, how the universal properties of the exponential objects are specified and so on, you can check that out in the document in the description. I'm just trying to give a kind of outline and show you all the rules of this simple type theory. Okay, so these are our final lot of rules. These are the final kind of equational rules we want to have. So this is the one for the empty type. It's the uniqueness principle for the empty type. And what it says is that if we have a context gamma and there we have a term of type, a term e of type 0, and if we also have a term x of type a, then in this context gamma we have this interesting result that if we do this abort on e, then we get a term of type a which is actually going to be equal to x. So this is really a very interesting idea. It's basically saying that if we do this kind of abort, this kind of null function on any value in the empty type, we get something that's equal to any value in a. So it's a strange idea. It's kind of saying that if we did have any value in the empty type, which we don't, but if we did, then we could do this function on it, this function which actually we know is vacuous, but again, if we did have a value and if we could do this function, then the output would be equal to any term of the sort of target type. Okay, so we have this kind of way that, so it's a very kind of interesting result, which would kind of allow us to give us something that's equal to anything. The only thing that stops this getting very strange is that we don't really have any values in our empty type to actually do this abort operation on. Okay, so there we are. The other thing we need to talk about, the final thing, is the sum type. Okay, so this is the first computational rule for the sum type. And what it says is that if we have a context gamma and we have a value A of type capital A, and also if we have essentially a function u from A to C and a function v from B to C, well then in that case, when we sort of form this function, well, I like to write it as u comma v in square brackets, so it's this kind of piecewise function. This is telling us that it sort of acts the way it should do. It's telling us that if we evaluate this kind of piecewise function on the left injection of A, then the results will be the same result as doing this function u on that value A. All right, so here's how we can think of it. If we consider this situation here, where gamma is just this context where we just say we have a variable z of type h, well then we can think that what this is saying essentially is that if we do the left injection on A here, and then we do this match function on that, then that composition there will be the same as the composition of u after A, which is this. Okay, so it's essentially saying that doing the match function after the left injection gives us u. And in a similar way, this second computation rule is saying that doing this match function here after this right injection is the same as doing this function v, where we have this function v specified here. So again, we can think of this in terms of operating these things on this input b here, this value little b of type capital B. And again, if we think about the context being z of type h, then we can think of it as this followed by this gives the same result as this followed by this followed by this. Okay, so it's basically just this idea that forming this sort of match function, this kind of intermediary arrow in our coproduct type, we can sort of think of it as a function which works like u on values that came from A and works like v on values that came from B. And then finally we have this other result, which is essentially telling us the uniqueness of this match function here. So what this is basically saying is that if we have a context gamma and we have a value s of type A plus B, and we also have this term m of type C that may depend on this value h of type A plus B. So basically, if we have something like a function like this, m here, then what this is basically telling us is that if we form this match function here, and the u that we use here is m after the left injection, and the v that we use is m after the right injection, then basically m is going to be the same as our match function here, or more precisely, doing this match function on this value s of type A plus B is going to be the same as doing m on this s. Okay, so a way I like to think of it is this is basically giving us our universality condition for coproducts. So essentially it's sort of saying that if we have this kind of match thing, which is based on a function u from A to C and a function v from B to C, and we basically have that this m here looks like this match, it looks like this intermediary arrow, in the sense that m after left injection equals u and m after right injection equals v. Well, in this case, if we do our match with our u and v, then that means that we can write this with the u replaced with this expression and the v replaced with this expression, and that this match thing that we have here is actually going to be equal to our m. So in a sense, this is sort of like saying if it looks like match, then it is match. It's this kind of universal property. So I thought I'd end this video by trying to demonstrate that these kind of ideas really can be implemented in computer code. So I'm not an expert in JavaScript, but I've tried to code something up in JavaScript to illustrate how these ideas work. And the reason I chose JavaScript really is because it can be used in a lot of different sort of practical contexts, and also it's kind of quite far away from the normal sort of functional programming languages and languages with their own type theories, which I actually prefer, but those kind of languages are already so close to the kind of thing we're trying to implement that it makes it too easy. So JavaScript, the idea I'm using here is just this sort of idea of making objects. So basically an object, so something like this, for example, can have different sorts of data attached to it. So this is this idea of key value pairs. So basically, we're sort of attaching different data to this thing, which in this case is called richsimp.emptyContext, and it has one key called kind and another key called entries, and these are sort of different slots that we can attach data to. And so I'm attaching this data called context where it says kind, and I'm attaching this empty list where it says entries. So this is a typical kind of way of storing data when you're programming in JavaScript, and then you can recover the information. For example, if I go into this console here, I have to simple type theory.richsimp, and then if I go .emptyContext .entries, I press enter, you see it returns this empty list here, because this is digging out this data which we've stored here. And so basically we can use this type of object-orientated approach to store different information. And our goal is going to be to basically implement this application of this rule here. Okay, so we want to tell the computer we have these inputs, and then we want to apply this product introduction rule here. So I'm going to show you the code for this rule and how it's implemented. And basically the idea is that we're going to make a function in JavaScript that takes in two inputs and checks that they have the right form, and if they do, it outputs something of this form here. So the first thing we'll do is define our inputs. So we want to define this empty context because in this example I want to implement, you see our input judgments that don't have any context. Thought that would make things simpler. So we set up this idea of an empty context. It's some data of the kind context, and it involves this empty list of type declarations. And then we want to have our first term. So we say that that's a term. We don't bother giving it a label. We say it's named A. And we also want to talk about this type, capital A. And now we form our first type declaration. So we're declaring that the value, which is this example term 1 here, is of this type of example type 1 that I've defined here. So this is our first type declaration, and this is basically this information here. And now we're going to form a judgment. So a judgment involves giving a context, which in our case will be the empty context, together with a declaration. So here's how we're describing our first judgment. And we're also going to set up our second judgment here, which is basically saying that little b has type capital B. And now we want to give this actual product introduction rule, okay? And so this is actually this function which takes into judgments. And the first thing we want to do is to do various checks to make sure that the inputs have the right form. So I don't want to get too focused on the details here. I'll put a link where you can find this code and look at it at your leisure. But basically, we want to check that the two inputs that we give are indeed judgments. And they're actually judgments about type declarations. They're not judgments about equalities or anything. And also that these two judgments have the same context. And if they do, then we're going to build this kind of output judgment, make sure that that has the right form. So yes, we have these various different checks that the inputs are judgments, and if these checks fail, then we'll output appropriate error messages. And also we want to check that the judgments are about type declarations, and also we want to check that the contexts involved in these inputs are equal. And then if they are, then we start to build up the outputs. So we want to make this kind of pair term where we're sort of saying the thing is a term. We'll call it a pair, so we'll give it this kind of label. We'll give it a name. So the name it's a pair involving the sort of names of the two inputs. And we store what's the first entry in the pair and the second entry in the pair. And we also want to set up the type of this output. So we'll say it's a type and it's a product, and it's built using the types of the things that were in the inputs type declarations. And then we can just build up our outputs declaration. It's going to be a type declaration of saying that this pair term has this product type. And our output judgment is just we can get one of the input contexts and attach this declaration which we've built. And so here's an example of using this this product introduction rule on these judgments which I've created. So if we go to the console, we can actually look at this structure. Here it is, and then if we open this up, we can have a look. So we see that this thing that we've made is a judgment, so it has a context and a declaration. So if we open up the context, we can see that it has some entries. In fact, these entries just form an empty list, and it also involves a declaration. So the context of this judgment that we generate is basically empty. But if we have a look at this declaration, it's a bit more interesting. So it's saying that the kind of the thing that we make is a type declaration, and the sort of value that we're having is it's a pair. It's called pair little a little b. It's a term, and it sort of has a first entry and a second entry, which are referring to the terms little a and little b. And that this thing has a type, and it's of course going to be of this product type. So this is just a sort of quick kind of sketch of an idea of how we might implement such as this product introduction rule. But you know, if you look at this a bit, you can kind of see that it's actually fairly straightforward to implement these kind of rules in a computer, just by checking that the inputs have the right data structure and sort of essentially applying the right kind of rewrite rules. and then one can string together lots of these functions basically to kind of emulate the construction of these sort of proof trees, really implement all of this theory, this simple type theory, in a very simple way inside a computer. And of course one can do the same thing with more elaborate kind of dependent type theories and so on.